Hi, everybody. Oh, I have to talk really quietly. So today I'll be talking about the evolution of giant planets and rocky planets. It's a pleasure to be back here at the Sagan Summer Workshop. I've been coming to this workshop and the Michelson Workshop for a long time, and so it's always fun to be back. So I'll spend about 3/4 of my talk talking about giant planets, in the last quarter talking a little bit about rocky planets as well. So we're here for a direct imaging meeting, and so evolutionary models are particularly important when you're thinking about trying to characterize giant planets. So for image planets, there we go. For image planets, as a lot of you know, masses are pretty rarely dynamically determined. Sometimes they are. So often a mass comes directly from some sort of evolution model. So your mass estimate will come from measuring the magnitude of your object in one band or in several bands, or if you have a spectrum, trying to determine the effective temperature of the object. And combining that with an estimated age, we'll talk about why it's hard to understand ages coming up next. And if you combine those two things, some sort of brightness or effective temperature estimate combined with an age, you can estimate the mass, and that comes from model evolution tracks that aim to understand the cooling of objects with time, their effective temperature over time, or their brightness in a bandpass over time, for a grid of masses. And so what these look like are things like this. This is from the Kondo 3 models from Baraffe et al. So I think a lot of you have probably been to this website. So there's a time in gigayears. This is 100 million years. You've got masses. This is 0.001 solar masses, which is about 1 Jupiter mass, because there's a factor of 1,000 difference or so. And so you can look up a certain mass. Let's call this about 10 Jupiter masses. At this age, there's a temperature estimate, log of the luminosity, log of the surface gravity, radius, and the absolute magnitude, a bunch of different band passes from V band out to M band. This drives home a point that Travis made yesterday, and that is to understand an evolutionary model, you absolutely have to have some sort of atmosphere model. To understand an atmosphere, you don't need to have an evolutionary model. But to understand the evolution, you have to have an atmosphere model. Because what an atmosphere grid, what an atmosphere model, what the upper boundary condition tells you is for a given structure model where you have the mass, radius, and density as a function of running through the entire planet. What you don't know is what the luminosity of that object is at the top of the model. And so that's what the atmosphere model tells you. It tells you what the effective temperature is of some structure model that you computed. It also helps you figure out the amount of time you're taking between successive structure models as you go from some sort of hotter start to colder and colder and colder as time goes on. So any sort of evolution model that you see has to be paired with some kind of boundary condition. The best ones are paired with a full range of models that are non-gray, that actually use wavelength-dependent opacities. And so you can generate cooling curves like this. This is a famous, very nice color-coded plot from Burroughs et al. 2001, which I think a lot of you have seen. This is log of the luminosity, and this is log of the age. This is 1 million years up to 10 billion years. So this is color-coded by the things in blue are more massive than about 75 Jupiter masses. And so these are things that are the lowest mass stars, the lower half of the M stars. And you can see these things might actually take hundreds of millions or even 1 billion years to land on the main sequence. And then these objects will burn for maybe even 1 trillion years. These objects down here below about 75 Jupiter masses, maybe about 13 to 75. These are the brown dwarfs. These are things that are not going to stably burn hydrogen into helium, and they're just going to cool over time. These magenta dots, is there a different laser pointer? All right. The magenta dots are where lithium burning is halfway gone. So lithium burning has a very negligible effect at all on the evolution, but it does have an observational effect. So if you can see lithium in your object, then you know it hasn't been burned yet. These gold dots are actually where deuterium burning is 50% completed. So you can see at about 13 Jupiter masses, that's the boundary between not burning half your deuterium and burning essentially all of it. And so you can see that deuterium burning does affect the evolution. It's an important energy source for a while. It props up the cooling curves for a while until that gets burned away, and then these things just cool off over time. Below about 13 Jupiter masses, these are things that we might call planets. If you like a 13 Jupiter mass definition for a planet or a brown dwarf, I do not, but that's fine. These are objects that form warm, of course, and then cool off over time. So this is 1 Jupiter mass. This is 0.3 Jupiter masses, like a Saturn mass. And you can see these objects essentially don't burn anything, and so they start out warm and they cool off over time. This, of course, drives home the point that if we want to directly image planets, we should look when they're young, because they can be orders of magnitude brighter. Jupiter now is about 10 to the minus 9 times the luminosity of the sun. Jupiter, when it was young, was closer to maybe 10 to the minus 5, so it's about 4 orders of magnitude right there. We're thinking about calculating evolution models. I think most of you guys have probably taken a stellar structure and evolution class. Most of you guys are grad students or older. The equations of stellar structure, of course, you've got the pressure, radius, temperature. Most of these objects we think are fully convective in their interior. So the temperature gradient in the interior isn't the radiative temperature gradient. It's actually just the convective adiabatic temperature gradient, so it's simpler. But the equation of interest when we're looking at the thermal evolution is this equation down there. So where is your luminosity coming from? And so for a star sitting on the main sequence, it's essentially a fairly static object. And so this term on the right is essentially 0. And for a star, you have some energy generation rate from fusion. This is a little epsilon here. For a giant planet or something that's not doing any fusing, this term is actually going to be 0. And your entire luminosity is going to be coming from cooling and contraction of your interior. So that's this term over here, temperature, and then ds dt, where S is the specific entropy. So the entropy is, of course, a quantity we hear about in physics all the time, but it's hard to have a good feel for it. At least I don't think I have a good feel for it. But one of the nice things about entropy is that you can track 2 things at once. So TdS is actually equal to dq, the heat. And so by tracking TdS, you can actually look at 2 terms simultaneously. One is the loss of internal energy, U, and one is PdV work from the contraction of the object. So by just tracking entropy, you can track these 2 quantities at the same time. And so for a giant planet that's cooling over time, there's no energy generation rates, and there's just this term. For a more massive object that's also fusing deuterium for a while, let's say over here, you'll have both these quantities participating. And as I mentioned before, what's really important for an evolution model is the atmospheric boundary condition. Because for a fully convective object that's efficiently convecting, convection is really easy. It's really easy for convection to transport energy up to the surface. But what convection can't do is get that energy out into space. At some point, you have to convert that energy to photons, and that's a very inefficient process. So you can think of a giant planet as being a really efficient energy transporter down below, but there's a bottleneck at the surface, and that is the atmosphere that has to let that energy out into space. There's a nice stellar tie-in, which I cover when I teach stellar structure to the grad students, and that if you look at the Hayashi track on an HR diagram, that's the region of phase space where fully convective stars sit. And one of the things you can show in that region of temperature luminosity space is that fully convective stars sit over there really in a particular region that only has anything to do with the opacity. And so fully convective stars are governed essentially just like fully convective giant planets. Their atmospheric opacity dictates where they sit in an HR diagram and how they cool off over time. So if you look at Kippenhahn et al., section 24.2, there's a nice analytic model of the Hayashi track of where fully convective objects sit based on the fact that their atmospheric opacity dictates their cooling. So there's a lot of different models you can use. I don't want to spend a ton of time on this, but I thought I'd give it a slide. Again, the upper boundary condition is important. And so that actually kind of tells you about the generation of model that you're using. These evolutionary models for brown dwarfs go back to probably Burroughs et al. 1993 and probably before. So the most commonly used ones are here. And so one is Burroughs et al. 1997. That's kind of a classic paper, but I would say it's kind of showing its age to some degree because we've learned a lot about the atmospheres of brown dwarfs and giant planets in the past 17 years or so. So that grid doesn't really include clouds in a meaningful way. A lot of it's using old atmosphere models that are not wavelength dependent. And so you're going to actually be inaccurate when you're trying to assess the cooling history using a model from that heritage, I would say. There's a very nice update from Spiegel and Burroughs 2012 that look at giant planets below about 10 Jupiter masses. Another widely used grid, because they're easy to find on the internet, and they're very, very nice papers, were Chabrier 2000 and Baraffe 2003. These are two different sets of models that look at the cooling history, one using a boundary condition that kind of maximizes the importance of dust and clouds in the atmosphere, and another end member where the chemistry is calculated the exact same way, but the dust opacity is just artificially removed. These are kind of limiting cases for how important dust might be in the atmosphere. And so those are also widely used, but it is an approximation in terms of the chemistry, thinking about how important dust might be. Another transition as we go from older to younger is Simon and Marley 2008. So those are evolution models that use upper boundary conditions that include a cloud layer for the warmer objects. And then when you switch to objects that look like they're cloud-free, they switch the upper boundary condition to cloud-free cloud-free atmospheres. So it's trying to reach something that's kind of self-consistent, using clouds when they're appropriate, not using clouds when they're not appropriate. And so if you look at what these do in terms of this is the log of the luminosity versus time, you can see that, well, they're not too different in terms of luminosity. But what they can be different at is you're looking at a particular bandpass. If you want to know, let's say, the L prime luminosity as a function of time, you're going to get very different results for these different models because they actually use different atmospheres. So the spectra that they would emit are actually be quite different. And so one of the things I'll talk about is how we're testing these models for a variety of objects. One other thing to keep in mind that's actually kind of interesting is that all these models for brown dwarfs and giant planets, they all use essentially the exact same input physics in the interior. So these models really only differ in their atmospheric boundary condition. There was one equation of state for hydrogen computed about 20 years ago now, and everyone's used that since because it's the best available, and it goes over a very wide phase space. And so if we do start to show cracks in how models compare to data, the first thing to think about is atmospheres, but of course the second thing to think about is some of the other input physics, because we might need to revise the stuff we use in the interior of the models as well. So a good question is, do the models work? Everybody wants to know that, and the answer is, well, we don't really know yet. We don't really have a lot of objects to compare to. They do for Jupiter, so that's good. Jupiter's an actual giant planet that's close to home. The only problem is that it's really old, and so it's not really like a directly imaged planet you'd want to look at. So one of the things I spend my time on is worrying about some solar system planets from time to time. And so you can compute evolution models of Jupiter. So this is the effective temperature versus time. And the red and black curves are two different atmospheric boundary conditions. One's from the 1970s and one's from a couple years ago. And you can see, well, they're pretty similar, but we can reach Jupiter's effective temperature at 4.5 billion years within a couple degrees. So that's great. That's really spot on. Saturn's a little bit too luminous today, which if you ask me in the Q&A, I could mention it has to do with helium rain, but that's only important for really cold, old planets. But again, Jupiter, we expect it to be quite a bit more luminous when it was younger, perhaps 800, 900, 1,000 degrees. So this is an object, Jupiter, 1 Jupiter mass, 4.5 billion years old. We do pretty well for that particular object. But of course, we'd like to know how this works at 5 Jupiter masses, 10 Jupiter masses, 30 Jupiter masses, at all different ages. We really don't have the cases yet to compare those two. There are a growing number of what you might call benchmark brown dwarfs, where you can have a very well-determined mass, a pretty well-determined age. If you get a spectrum of the object, you can also determine its effective temperature. And those are key quantities then you can then compare to what you expect from a model. So these benchmark brown dwarfs are really becoming important. There's a nice paper by Dupuy et al. 2014 that suggests that, that models underpredict the luminosity of cloudy L dwarfs by about a factor of 2, which is, I think, a big deal. And so if that's true, that would lead you to have about a 30% error on the mass if you're trying to estimate the mass just from an evolution model. So we have a very small number of objects. I think there's 2 or 3 objects that this has been done for, but they're all kind of consistent in that the luminosity is underpredicted. So if the sample size grows to 5 or 6, we'll certainly have to give this really serious thought about what might be wrong with the evolution models. So far, there really hasn't been a lot of free parameters to tune. There's your atmosphere models, the same atmosphere models you use to compute spectra to compare directly to observations. And so those are the actual grids you use for the upper boundary condition. And so if the atmosphere models we think that we're using to compare to spectra generally fit the spectra pretty well, well, they should be pretty good as the upper boundary condition. So if that ends up not being the case, it'll be quite interesting. On the right is a nice plot from Burrows et al. 2013. This is the mass-radius relation of brown dwarfs. I picked this plot because it also drives home the point that the atmospheric boundary is important. So this is at an age of 3 billion years. The green are the Burrows 97 tracks. In red are cloudy models, and black have no clouds. And so basically, and then there's also metal-rich, metal-poor, and solar metallicity. And the basic point is that all these, in the interior, all these models are equal, but they all have a different atmospheric boundary condition. And so what this paper shows is that you can have about a 15% difference in the radius at a given age, just based on if your atmosphere is fairly transparent and the object cools off fast, or if the atmosphere is a really thick cloud opacity, which keeps the planet from cooling off very well. We're, of course, looking at strongly irradiated objects all the time, transiting planets, transiting brown dwarfs, and that's another test of evolutionary models. But it's a very different phase space compared to directly imaged planets, because transiting objects are generally very old, they're extremely strongly irradiated, so it's not necessarily a great test when we're comparing to directly imaged young planets. Okay, so we've heard a lot about initial conditions and hot start versus cold start, so I wanted to spend about 15 minutes talking about this because it's particularly interesting for young giant planets that we might directly image. So I'll move into that phase of the talk. So this is just a plot of a log of the luminosity versus the time in millions of years. This is just the first 5 million years. These are 6 different model planets. The dotted lines are what you might call a hot start, an arbitrarily warm start over here. And the other curves are from a core-accretion formation model, one particular flavor. So we'll talk about that for a while. Okay, so initial conditions are extremely important if you're at a young age. And they're important for directly imaged planets. So the standard cooling models that I've talked about, Burrows tracks, Baraffe, Sagan tracks, these standard cooling models for giant planets and brown dwarfs, they make a number of simplifying assumptions. And they make these just because it's computationally easy, which is fine. You've got to be honest about these things. So planets begin their evolution fully formed. Planets are adiabatic at all ages. They're fully convective at all ages. They're initially arbitrarily large and arbitrarily hot. And so what the initial model you choose isn't really that important as long as it's really hot, because your Kelvin-Helmholtz time goes as 1 over the luminosity and 1 over the radius, both those things. So if you pick an initial model that's really big and really hot, it's going to cool from that state really fast, maybe hundreds of years or thousands of years. And so if you only plot your model 1 million years and later, it's not really going to matter what the initial model was that you picked. Because then, so all these plots you'll see, they only often get plotted for ages greater than 1 million years or so. And the basic idea is that, well, if you don't worry about the very, very young ages, your initial conditions probably don't actually matter. That's at least the assumption. But people have been thinking about planets for not just the past 5 years or 10 years. It's actually people have thought about this for many decades. So Dave Stevenson is a professor at Caltech here on campus. And he wrote a classic review article in 1982 thinking about the evolution of the solar system's giant planets. He had this great quote that, although all these calculations may reliably represent the degenerate cooling phase, they cannot be expected to provide accurate information in the first 10 to the 8 years of evolution because of the artificiality of an initially adiabatic, homologously contracting state. And so this is true. And so this particular quote, when I was a grad student, really stuck in my mind because I was reading lots of the literature. And so when Mark Marley and I were working together at NASA Ames thinking about evolutionary models, he also remembered this quote because Dave was his undergrad research advisor. And so we were thinking about how to do a better job of maybe understanding the early evolution of planets. And so Peter Bodenheimer is a retired professor at UC Santa Cruz, who I know well, and Jack Lissauer is also at NASA Ames. So they have one of the best implementations, we think, of core-accretion planet formation. And so in this particular representation of core-accretion, this is a nice plot they made that shows 4 panels. And so the upper left panel is the mass in Earth masses. This is time in the first 4 million years. These are all the first 4 million years. And so in this model, they form about a 10 Earth mass core quite quickly. The solid line is the solid's mass, the dotted line is the gas mass, and the dashed dot line is the total mass. And so what they essentially find is after you build up about a 10 Earth mass core that starts to accrete quite a lot of hydrogen and helium, and you reach a runaway where you start to grow really large, you might accumulate hundreds of Earth masses of hydrogen and helium. The bottom left panel is the mass accretion rate. So the solid is the solid accretion rate. So you're building up ice and rock into a core. And then the dotted curve is higher. You're growing in terms of gas faster than you're growing the amount of solids. And this spikes up to a runaway where you accrete hundreds of Earth masses of hydrogen and helium in a small amount of time. So what this does in the upper right, this is your luminosity. So you're a little bit luminous when you're building up your core, then you're kind of static for a while. And then when you reach this runaway of gas accretion, you accrete a tremendous amount of gas in a small amount of time. You get a huge luminosity spike. And then what happens after that is they artificially cut off accretion, like a knob they tune down. And then the planet after that is much lower luminosity, and it cools off for billions of years after that. And so the lower right panel is the radius, so the solid line. This is log of Jupiter radii. So this is the core at about an Earth radius or so. The solid line, so the solid dashed line, is the capture radius, at what radius you could actually capture planetesimals, which leads to this solid curve still being here. You're still accreting some solids. And then the actual surface radius here is around about 100 Jupiter radii, a big fluffy object. And then when they turn down accretion, there stops being energy input, and so it just kind of collapses into a smaller object at around 1.5 Jupiter radii or so. Okay, so this is one-dimensional implementation of core accretion, which is, of course, a three-dimensional process of how planets form. And the key to this whole high luminosity phase and low luminosity phase over here is the boundary condition. So this is not an evolutionary model boundary condition. This is a planet formation boundary condition. So this is borrowed from an old stellar evolution context from Staller et al. In 1980. And so what they assume is that a shock happens in their one-dimensional model. So they assume gas comes in with a fairly low temperature. It's shocked to a tremendously high temperature. That energy is radiated away. That's what this spike is here. And then the gas that's actually accreted onto the planet has already, you can think of it as the mass is coming in from infinity or coming in from far away. It has a lot of potential energy. And that's brought to the planet. It hits this shock, and that's radiated away. It's gone. So then when you accrete the gas after that, it's cold, low entropy gas. And so that's why the start of the evolution phase is quite cold, because you've essentially lost all your accretion energy in this spike. And so that's an assumption that they're making in their one-dimensional treatment of core accretion. We don't yet know if this is correct or not. This is really the entire reason why a cold start or a core accretion start is the lower luminosity starting point. And so in the Marley et al. 2007 paper, we spend quite a bit of time talking about how this particular phase of formation leads directly to lower temperatures at the beginning. So if we look at the specific entropy of the interior for hot start models versus what we called core accretion start models, you can see Jupiter's down here. It's old and cold, but Jupiter, when it was young, had a hotter interior. And so what you would expect normally is as you go to more and more massive planets, you expect them to have higher and higher internal temperatures, higher and higher specific entropy. But in this particular implementation, you actually get what looks like a tuning fork diagram. As you go to higher and higher masses, more and more of your material had to come in through that shock. And so you kind of asymptote at kind of a lower amount of entropy. So this is plotted here as the entropy about 1 million years after formation. And so, again, it's quite dependent on the treatment of the accretion shock. And so what you get are evolution models that look like this. This is the radius in Jupiter radii, the effective temperature, and the luminosity. This is 1 million years out to, 5 billion years. The dotted curve are the arbitrarily hot starts. The solid curves are this cold start, this core-accretion start. And so the model core-accreted planets are formed with significantly smaller entropy and radii than the hot starts. Because the Kelvin-Helmholtz time goes as 1 over L times R. If your luminosity is tiny and your radius is tiny, your Kelvin-Helmholtz time is going to be long. So it takes a very long time for these models to evolve. They kind of stay where they were. It takes a long time for them to change because they're low luminosity and small radius. The initial conditions are not forgotten in just, quote, a few million years, but rather 10 million years to a billion years. The planets all kind of cluster at a very young age. But to reiterate, the entire effect depends on this particular treatment of accretion. And so in reality is probably somewhere in between. In the Marley et al. Paper, there's a discussion about how this initial condition is probably about the coldest start you can imagine because you've essentially given away most of your accretion energy in this shock. And so it's quite hard to make a planet much colder than this. Whereas this is arbitrarily hot, this is really about as cold as you can imagine making your planet. So there's been a lot of work in the past few years looking at this topic. So Marley and Fortney et al. Looked at the evolution and spectra of these hot start and colder start models. Spiegel and Burrows looked at a variety of cases in between the hot start and the cold start. Mortacini et al., the paper from last year, looked at how you could convert what you might expect to be a cold start into something closer to a hot start just by accreting more planetesimals. Because what's happening then is you're just adding more and more gravitational potential energy at a young age. And then Marlowe and Cumming had a nice paper that just got accepted to monthly notices this year that looks at a variety of cases and how you might be able to ascertain what kind of start you had by looking at the luminosity at a young age. There's also been papers that have looked at the effects of deuterium burning. So this is interesting because these models stop at about 10 Jupiter masses. But you can imagine if you want to go to 12 Jupiter masses, 14, 16, you're going to have deuterium burning turning on. So these two papers look at how deuterium burning is different between a hot start and a colder start. And there's a really nice paper by Baraffe et al. 2002 that looked at this kind of idea of how initial conditions affect the properties you think you're obtaining for a young object by comparing models to observations. She looked at a variety of starts for brown dwarfs, the brown dwarf context. This is another paper that's very interesting you should look at, and how initial conditions affect the early evolution of brown dwarfs as well. So the question is, what is the status of models versus reality versus a hot start or a cold start? And really, it's kind of too early to tell. This is a really nice plot, though, from Marlowe and Cumming 2014. This is log of the luminosity versus time. And in red, they have some versions of hot start planets. In blue, they have kind of an arbitrarily lower initial entropy, a colder start. And they looked at the literature. They looked at all the objects that were claimed to be directly imaged planets or brown dwarfs from about 1 to 25 Jupiter masses. And they just stuck them on this plot based on age estimates. And what they find basically is, well, these things kind of cluster along the red tracks, the hotter start evolution models. So that might suggest that a hotter start is probably more realistic. Although keep in mind that perhaps none of these objects actually formed by core accretion. A lot of these objects are isolated brown dwarfs. Actually, most of these objects are. And so it's not really a definitive match. And I certainly would advocate what Travis mentioned, that you can't just plot an object on here and tell how it formed. What I would say is that instead of thinking about hot start versus cold start, they're really the most extreme end members you can imagine. How warm the start is an important clue regarding the energetics of accretion. I think that's the most important takeaway point. And that's really what we should be trying to understand for these really young objects. You might ask the question of, well, why can't we just run the model and see what happens? And in 3D with radiation and hydro and stuff like that. And you can, but the problem is that you've got two problems. One is the problem of scale. You've got gas coming in from hundreds or thousands of Jupiter radii, and you've got a core that's about the radius of the Earth. And so you want to see what happens to gas that's accreting onto that object. You also have a problem of time scale in that you can't just follow this really for a year or 10 years. This formation time can take millions of years, so you actually want to be able to follow this for millions of years. So it's computationally really challenging in 3 dimensions to do this for a long period of time, to actually see what the energetics of accretion actually are in the core accretion scenario. So that's why these one-dimensional formation models are still so widely used that you can actually follow this for millions of years, where you can't really do that in a simulation like this. So I want to switch gears and talk a little bit about young rocky objects. So there's not as much work that's been done, but it is a cool thing to think about. So the key take-home message, I would say, is that giant impacts are the generic end of rocky planet formation. And so this is a nice plot from Raymond et al. 2006. This is eccentricity versus center-major axis. And the colors are a color coding the amount of water. So if you're close to the parent star, you're inside the ice line, you have rocks. If you're further away, you're beyond the ice line, you're watery. But the point I want to make is that, let's say you're at 30 million years, okay, you've formed things that might be like Venus and Earth, but you've still got tremendous amounts of lunar-size and Mars-size objects still flying around after 30 million years. And so rocky planet formation can take 50, 100, 200 million years to be finished. And so the generic outcome is that some of these objects are going to smash into the planets you have already. And so we shouldn't think of the moon-forming impact for the Earth as a rare event. It might have been rare that it was glancing enough that it squirted out this material that formed the moon. But giant impacts are really what rocky planet formation is all about. And so you might imagine then, you might have a hot, glowy object, right? So we can think about what the Earth might look like. This is just an artist's rendering, of course, of what the Earth might look like after it was smashed in a giant impact. It's hot. So that's good. We want to see things that are hot. But just because the surface is hot doesn't mean that the object has a high effective temperature. Just like Jupiter's core is 20,000 degrees, but we see Jupiter as a 125 Kelvin object. We can't necessarily see down to the hottest part. We can see down to an optical depth of 1. So this is a really nice paper by Kevin Zonley and his collaborator Zonley et al. Called Emergence of a Habitable Planet. It's in Space Science Review. I really recommend it. It looks at Earth after the moon-forming impact, and then the first billion years or so, and how the Earth came to be a habitable environment. And so this is a somewhat complicated diagram, but there's a few things I want to point out. This is a time from 100 years out to 1 billion years, many orders of magnitude. We've got a rock vapor surface, a soft magma ocean, a hard magma ocean. This is temperature in Kelvin. And so you can look at the surface temperature here. After the impact, very hot, 3,000 plus, 2,000 plus for a long period of time, maybe out to 1 million years or maybe a few million years. That's interesting, right? So it's possible we could look at young star-forming regions. We could see objects. 1 million years is a reasonable amount of time. But what happens in this particular simulation is that when you smash a Mars-sized object into the surface of the Earth, you liberate a tremendous amount of volatiles that were stuck in the rocks. So you make a really thick CO2 and water steam atmosphere, so that your radiating temperature is quite a bit lower, only about 250 degrees, even though your surface temperature is over 2,000 degrees. So that's why I compared it somewhat to like a giant planet, in that there's a hot surface way down below, but you can't see it. In this particular simulation, eventually the planet gets cold enough that your steam condenses, and you end up making an ocean, and that ocean dissolves the CO2, and that kind of makes the atmosphere we have today to some degree. But in its young time, when it's hot, you can't actually see the surface. And so Roxana Lupu, who's a postdoc at NASA Ames, she led a paper that looked at what the spectra and atmospheres of post-impact Earth might be. Okay. And so these are different compositions. This is continental crust, vaporized, bulk silicate Earth, vaporized, and surface pressures of 10 bars or 100 bars. And so you can see that, yes, the surface can be 2,000 degrees, 1,500 degrees, but in the part of the atmosphere that we see, we're much colder, 200 or 300 degrees in all these models. So you can't see down to the surface. In terms of spectra, this is a plot of brightness temperature versus wavelength. So brightness temperature is one of my favorite units. It's if you're looking at a particular amount of flux at a certain wavelength, if you imagine that flux is coming from a black body, what is the temperature of that black body that would cause you to see that flux? It's essentially analogous to what is the temperature at the tau of 2/3 surface that you're looking down into. So it tells you about the temperature that you're looking down to in the atmosphere. And so if you had this is a model with a 1600 Kelvin surface, if you could see down to the surface, the brightness temperatures would be 1600 degrees. You could see the surface. So these are two of the same models. This is two models from Roxana's publication, Lupu et al. This is a calculation by Miller-Ricci et al. 2009 looking at a similar situation. The Miller-Ricci models actually didn't include, we think, enough opacity in the atmosphere. So you could see quite a bit more deeply in their models compared to the Lupu models. So you can see quite high fluxes. You can see high temperatures. In the Lupu et al. Models, we think we did a better job, at least of incorporating all the opacity sources. And so you can't see as deeply into the atmosphere. So you're looking at temperatures from about 300 degrees, 200 to 500. And so we can take these models and we can actually calculate where these planets might fall in the color magnitude diagram. So Caroline Morley made this plot of absolute H-band magnitude versus H minus K. And you can see up here, this is the bottom of the M dwarfs, the L dwarfs, the L to T transition, and T, and at the T to Y transition down here. And these are a bunch of models that were run, again, for different surface pressures and different continental crust or bulk silicate Earth compositions. And this is essentially where these objects fall. And you can see there are many, many orders of magnitude below where the coolest directly imaged planets or brown dwarfs are. So if you want to be able to see these, you have to be able to look at very, very faint objects. We're, of course, not quite there yet. So the promise of seeing young, post-impact smashed objects is cool. But if you want to see that really hot surface, you really have to get rid of the whole atmosphere. And it's not really clear you'd be able to do that. So to conclude, I'm good on time, I think. So thermal evolution models of giant planets aim to understand the post-formation cooling history. And that's, of course, extremely important in directly imaged planets where we often don't know the mass. You want to compare the observed quantities to model-derived quantities. The free/unknown parameters in giant planet cooling models mostly revolve around the atmospheric boundary condition. Just like when we're comparing spectra to known objects, we're trying to figure out the chemistry, the cloud opacity, things like that. Although it would be nice to have a new equation of state for hydrogen where we could compare how important that is in the cooling models. We don't have that right now. Model testing is just starting to progress, and it's coming from brown dwarfs with well-determined masses and ages. Also, the HR 8799 planets I didn't really mention very much. That's a system where there's four directly imaged planets. And brute force dynamical integrations of the orbits of those planets indicate there are probably around 5 to 10 Jupiter masses, whereas some of the model fits would indicate probably more like 10 to 20 Jupiter masses. So that's the case where even though we haven't seen a full orbit of the objects, you can run brute force integrations that tell you the masses are probably a little bit lower than we were expecting. So that's also a very nice check on models. For young planets, especially, the role of initial conditions are still being investigated, but cold start does not necessarily equal core accretion. We probably will find out someday that you can have a variety of cold, warm, and hot starts from core accretion. It's a little bit too simple to equate a cold start with a prediction of core accretion. That's one particular flavor of one-dimensional core accretion with one particular atmospheric boundary condition. The properties of hot rocks are still being explored, but we are unlikely to see the hot surface just because of the energetics of accretion. You're going to liberate a very thick atmosphere, and that's going to block you from seeing the hot surface down below. That's it. Thank you very much. Maybe I just put this backwards. Well, I guess, the question is, what sort of non-accretion process could mimic cold start? I guess what I would say is that we don't know that cold start actually happens. It might be that core accretion is also something similar to a hot or warm start. And so it's possible that a truly cold start, like has been published, doesn't actually exist. I think that's the simplest way to put it. The point of the paper was really, initially, was just to explore how the evolution varied with initial conditions. And so we actually saw that it can vary a lot. The question was about how the assumptions of an adiabatic interior and other topics and other things related to following the entropy, how does that relate into the actual calculations as a function of time? I should mention that it's not a truly adiabatic interior. There has to be some very slight super adiabaticity, because if it's truly adiabatic, then you're not going to actually transport energy. So in reality, there has to be some tiny super adiabaticity when you actually do mixing length theory or a calculation of what the super adiabaticity is, the increase in the temperature gradient above an adiabat. It's extremely tiny. It's probably, people have found it's maybe like 10 to the minus 5 of the adiabatic temperature gradient. So convection, we think, is so efficient that you only need a really tiny super adiabaticity to transport that energy out to the surface. It's possible, there's been a couple calculations in the past few years looking at this, that if you have a composition gradient in the deep interior, it's harder to dredge up your parcels of gas up to the surface. And so that actually might lead to higher super adiabaticities and would lead to a steeper temperature gradient in the interior. And that actually would change the cooling history of the planet, because it would be harder to transport luminosity to the surface. But I think the key answer to your question is that it's not exactly an adiabat, but for simplicity, you can treat it as an adiabatic profile, because the super adiabaticity is such a tiny increase over an adiabat. A lot of people have looked at, there is an assumption that I think is reasonably well-founded that a direct gravitational collapse planet approximates a hot start to some degree. So people like Peter Bodenheimer did a calculation like that in the 70s. Ravid Haled has looked at that. And so people modeled direct gravitational collapse. It seems to work better in cold parts of the disk, so like dozens of AU out. When people model core-accretion, they find it generally works better in a few AU or several AU from the parent star. So in terms of where the objects are, I guess I would expect further out in the disk, hot start to be accurate. That doesn't necessarily mean, I think, that hot start is inaccurate close to the parent star, because I'm not convinced that a cold start is a generic outcome of core-accretion. It's one modeled outcome of core-accretion.